Hello everyone. I welcome you all to the Amateur Astronomy Club seminar on our universe and the Big Bang Theory explained. We are excited to see many of you here today. Thank you all for joining in. I am Shilpa Shrivi, currently in second year mechanical and an AAC member. It is my great pleasure to introduce Professor V. Sreenath, who is an assistant professor in the Department of Physics in National Institute of Technology, Karnataka, NITK. I'll start off with a brief introduction. Professor Sreenath holds a PhD in physics from IIT Madras. He has been a postdoctoral researcher at Louisiana State University, US. He was a postdoctoral fellow at the Inter-University Center for Astronomy and Astrophysics, Pune, before joining NITK in the year 2019. He has authored a number of papers and has collaborated with several notable researchers, including Professor Abhay Ashtekar. Professor Sreenath is focusing his research on investigating various primordial scenarios such as inflation, loop quantum cosmology, and other bouncing scenarios. Thank you very much, so, for joining in and being a part of this session with us. We are really excited to hear what you have to share today. Now, before we start with the session, here are a few guidelines for the audience. I would request you all to please keep your mic on mute to avoid any disturbances in between. Feel free to ask your questions in the chat box. Don't hesitate. All the questions will be answered in the end during the Q&A session. Now, with all this said, I welcome Professor V. Sreenath to take over. Thank you once again, sir, for giving us your time.
Uh, Thank you for the invitation to give this talk. Let me share my screen. Thank you everyone for, thank you the organizers for inviting me to give this lecture. Um, so the idea is to give a flavor of what is cosmology. So I thought I will speak about our universe, um, a little bit tell you its main features of the universe, and then maybe try to build a model of the universe. Right. So it will not be a very detailed model, but it is the simplest model that you can construct think of about the universe. It's known as a Friedman model. Let's start our discussion then. Okay. So basically, the idea is that we will discuss what is our universe. We will talk about gravitation, why gravitation is important, and the current understanding about gravitation, which comes from general theory of relativity. Then I will put the first two sections, ideas that we gained from the first two sections together to explain. I mean, to tell you how we describe our expanding universe. We don't explain our universe. We just will will try to describe our universe using general relativity. Okay, and in the process, we will see that how we believe our universe started with a big bang. Okay, so basically, what is our universe? We live in Earth, uh, and Earth is one of the 8 planets in our solar system, right? And there are many other objects which revolve around the sun, but Earth is a planet revolving around solar system. Sun is actually average size star, maybe a little bit above average, but an average size star, and it is part of the Milky Way. Milky Way is a galaxy, and Milky Way galaxy is it contains about a billion or so stars. Sun-like and bigger and both bigger and more massive stars as well as smaller stars. Um, okay, so Milky Way is supposed to be what is called as a spiral galaxy. So if you look at the picture on the left hand side, you will see that there are spiral arms which extend out. So Milky Way is what is known as a spiral galaxy. When you see Milky Way, I mean, when you see Milky Way from Earth, you won't see the Milky Way in this shape. What you will see is a band of stars stretching from north to south. And now I think if you go to I think it's this time of the year, summer. If you go to a very dark place, you will be able to at night you will be able to see Milky Way. Now, Milky Way is also not alone. I mean, there are many galaxies. Especially Milky Way is actually part of a local group of galaxies. About 54 galaxies are there. It is known as local group. And Milky Way is one of the bigger galaxies in the group. So there are basically three big galaxies. One is Milky Way. Then there is Andromeda, which is this one, and Triangulum Galaxy. So the center of the local group is somewhere in between Milky Way and Andromeda Galaxy. So there are other 51 smaller galaxies. And if you look beyond the local group, what you will see is that this local group is in fact part of a bigger cluster of galaxies. It is so there are about 1,000 or so cluster galaxies in this cluster, and universe has many such clusters. So this how do we know all these things? We basically, there are people who have taken a telescope in this in the I mean taken a telescope and uh, is there a question or there's a no? Okay, fine. Okay, so there is so in this case of this picture, so basically this picture was obtained by a survey called as Sloan Digital Sky Survey, and so basically they had a 2-meter telescope probably. So anyway, so they had a telescope and they used that telescope to systematically scan over the sky, and I think they have finished about 20 years, and they have given us a very detailed picture of our universe, and the best detailed picture till date has been obtained from this survey. So I now request Aditi or Arpita to share the video that I had uh, sent you. So I will unshare my screen for now and request them to share.
Yes. So I'll share my screen.
This is the telescope of the Sloan Digital Sky Survey, operating since 1998. Scientists from all over the globe use it to study the sky and see all the way across the universe. Because of Sloan's advanced instrumentation, researchers can make detailed maps of everything they see. From here, we see the location of the Sloan telescope in North America. Starting next year, Sloan will use the DuPont telescope at its facility in Chile to study the southern sky. Just beyond Mars lies a belt of asteroids. Sloan charts thousands of asteroids, helping us understand their nature, origins, and potential risks to the Earth. Beyond the outer planets, as we leave our solar system, our sun becomes just one of billions of stars in our galaxy. Some of the stars Sloan sees are surprising. Binary white dwarfs that will someday explode. Sloan is also looking at stars with their own solar systems. How similar are they to our sun? As we move farther out, we now see a great citadel of stars arranged into spiral lanes. Sloan is mapping this galaxy we call the Milky Way, from its most ancient stars to stellar nurseries. Sloan's discoveries are helping reconstruct the Milky Way's voracious history of absorbing smaller galaxies.
Audio is there, right?
Now we see more small satellite galaxies. One day, they too will be coupled up. As we pass Andromeda, we behold the billions upon billions of galaxies in our universe. They form long strands and sheets, pulled together by dark matter with dark energy filling all of space. One of Sloan's goals is to survey these colossal structures of galaxies. By comparing the simpler structures from the ancient universe with our universe today, astronomers can trace the formation of galaxies like our Milky Way. At the largest distances, quasars provide beacons across the universe. Sloan is using the light from quasars to chart the gulf of space between us and them, extending our map of the universe farther than ever before. Thanks to our team of dedicated researchers, the Sloan surveys are writing new chapters in the history of astronomy and in our understanding of the cosmos.
Thank you. So I will share my screen now.
Yes, sir. Let me stop sharing. Okay.
Those who are interested, this SDSS, if you search Google for Sloan Digital Sky Survey, you will be directed to their website, and there are many more interesting resources available. So you're free to explore that. Okay, so basically, what such surveys have told us is that I hope I am audible now, right? Audible and my screen is visible.
Yes, sir.
Okay, so basically, what such surveys have told us is that the matter that is distributed in the universe, like galaxies, stars, galaxies, so they form a web-like structure, which is spread throughout the universe. So they are there as far as we can see, right? So this tells us that the matter in the universe is spread over the universe like a web-like in a web-like structure. And this web-like structure has two properties. One is what is called as homogeneity, which basically tells you that the web-like structure looks the same at every point. The second property is that it is isotropic, which means that regardless of the direction in which you look, it will look the same. So if you, to explain what I mean, so it doesn't matter whether you are here, if you consider a big sphere here, or a big sphere, another big sphere here, they will be, the contents in the density of the contents in that sphere will be roughly the same. In fact, you have to make a big sphere in the sense of about 100 megaparsec. If the diameter of the sphere is about 100 megaparsec, um, radius of the sphere is about 100 megaparsec, then you will see that regardless of where you put the sphere, you will have the same density of the universe, matter density of the universe. Similarly, isotropy means that regardless of whether you look here or in this direction or in this direction or any other direction, universe will largely look the same. Hmm? So this is a statistical property in the sense that clearly, if the density on Earth is not same as say density of matter around say Jupiter, there may be more mass there. But if you consider a big enough sphere where you average things, you will see that the universe is largely homogeneous and isotropic. So this is a key property that we take home from the Sloan Digital Sky Survey. So now there was a, let me take you to a discovery done in 1929
Excuse
by
me,
Hubble.
sir.
Yes.
Sir, what is the value of megaparsec which you told?
Parsec is about 3.26 light years. Mega is 10 raised to 6.
Okay, sir.
So what I said is 100 megaparsec.
Yes, sir. Thank you, sir.
Okay, so there was this discovery done by Hubble. Hubble was basically measuring the velocity of faraway objects, and he obtained this plot on the top right. So there is a distance on the x-axis and recession velocity. It's not very clear. Recession velocity of those galaxies on y-axis, and he got various points, and he fit a straight line through those points. A more updated figure is on the right, and the references from where I got those pictures are on at the bottom. So if you so we see that farther away is the galaxy, so distance shows that this is farther away, larger is its velocity, right? So this velocity is closer to, sorry, this galaxy is closer to us, So in fact, this is supernovae. So this supernova is closer to us. So it has about a few thousand kilometer per second velocity, whereas this, which is very far away, which is at 700 megaparsec distance, has about 40,000 kilometer per second recession velocity. So this means that a velocity is proportional, directly proportional to the distance of the galaxy, distance towards the galaxy or towards the object that we are measuring. So this proportionality constant is known as Hubble constant, and it tells you the rate of it is actually the rate of expansion of the universe. So it is possible that we can interpret this velocity, I mean this velocity distance relation, as telling us that our universe is expanding. Hmm? So this Hubble's law tells you that the velocity is expanding. I mean, universe is expanding. So there are, to summarize what we have done is we have seen that our universe has a web-like structure, and that web-like structure is homogeneous and isotropic. Also from Hubble's law, we know that our universe is expanding. So now, having described what is the nature of the universe, in the sense that how are matter distributed in the universe, let's describe what are the constituents of the universe. So I will broadly classify the constituents of the universe into three types. The first type is known as non-relativistic matter. Then we have radiation, and then dark energy. So this is an odd. I mean, when you first see this classification, you may think that this is an odd way to classify things. Basically, non-relativistic matter means matter which are not moving very fast. Then when you take radiation, radiation is like light or massless neutrinos which travel really, I mean, close to the speed of light or at the speed of light. Uh, so so um, so radiation constitutes very fast moving objects, and then there is dark energy. So the reason why we have chosen such a classification is because they are nicely classified by their relation between pressure and energy density. So non-relativistic matter are like ordinary electrons, protons, things like that. So they hydrogen, helium. So they are treated for, as far as our study is concerned, they are pressureless. Then there is radiation. Radiation has this particular relation: pressure is equal to energy density by 3. So there are derivations that I mean, you can derive these things from basic principles of statistical mechanics, but we will not go into those details. But basically, these are classified by their relation between pressure and energy density. Mass is matter, non-relativistic matter is pressureless. Radiation has P is equal to rho by 3, and dark energy has a negative pressure, and it is equal to minus rho. So this relation is between pressure and energy density is known as equation of state, and so they are P is equal of the form P is equal to W rho, where W equal to 0 refers to non-relativistic matter, W equal to 1 by 3 is radiation, and W equal to minus 1 is dark energy. So okay, so what are these non-relativistic matter? It is basically all visible matter and dark matter. So this is non-relativistic matter. Radiation consists of photons, neutrinos, and there is dark energy. Dark energy, we don't know what it is. Actually, the word dark in dark matter and dark energy are essentially saying that we don't know much about it. You can also interpret the word dark as saying that it does not interact with our visible light or the usual matter, basically coming from the particle physics, standard model of particle physics. So it doesn't interact with any such known matter. So in this sense, it is known as dark matter. It actually shows our lack of understanding about these things. So not recently, in 2013 there was a not actually. So in 2010 there was a satellite that was launched known as Planck, and its final results were out sometime last year, and they state that our universe has a large amount of dark energy, which is like about 70%. Dark matter is about 27%, and there is about 5% is the ordinary matter. So so when we say okay, so which basically tells you that about 90, we are unaware of of about 95% of our universe. So we don't know anything about dark matter, nor do we know about dark energy. So we don't know anything. We don't know much about the 95 percentage of our universe. Now, so what have we learned? So we have learned that our universe is isotropic and homogeneous. We know that our universe is expanding, and we know that our universe constitutes of non-relativistic matter, radiation, and dark energy. And the so I haven't shown radiation in this figure, but radiation is actually very tiny percent. So of today. So this is the constituent of the universe today. Hmm? Radiation is actually a very tiny percentage. Okay, so we know the constituents of the universe as well. So now we know roughly, we have a rough idea of what our universe is, and we need to find a way to model it. So in physics, you know that in order to model a system, you need to know what is the system, what are the things that is happening in the system, and also you need to have a governing force that is describing the system. So in the next part of this lecture, what I will do is I will actually describe. I will argue that gravity is what governs the universe, and then tell you a little bit of current understanding about gravity, which is given by general theory of relativity. Hmm? Okay. Uh, okay. So yeah. So basically, you might have studied in your 12th standard that uh, our universe. So there are four types of forces in the universe, right? So, so there are strong forces which binds the nucleus. There are weak forces which is responsible for things like radioactive decay, beta decay, and so on. Then there is electromagnetic force which binds atoms, is responsible for light, and then there is gravitational force which binds solar system and so on. Right. So we have studied about these four forces. Of these, the two on the left are short-ranged forces, and the two on the right-hand side are long-range forces. So the strong force is actually acts between quarks and other subatomic nuclei, subatomic particles. Weak force is also largely it governs neutrinos or beta decay and so on. On the other hand, long range forces, as you know, the electromagnetic force as well as gravitation, Newtonian gravitation, you know that the force is inversely proportional to distance square, and you know that they are long range forces. However, of these two, so we will rule out short range forces because clearly short range forces are not enough to govern our universe, because our universe is huge, right? It's bigger than anything that we have seen, so clearly, because we live inside it. Short range of forces we can rule out, and then if you look at long range forces, we can argue that our universe, we haven't detected any net charge in our universe, existence of net charges in the universe. So our universe is electrically neutral, and hence yeah, so there is no major electromagnetic force. You don't see the opportunity for electromagnetic force to play such a big role. um, so as far as the universe is concerned, that leaves us only one long range force, which is gravitational force, and gravitational force is always attractive. You cannot shield it, right? It has many unique properties, which I will get to in shortly. So gravitational force, of these four forces, gravitational force is the weakest, but yet it is the only long range force that can govern our universe. So that leads us to general relativity, because our current understanding about gravity comes from Einstein's general relativity. So there are, before we go to general relativity, I will tell you one or two aspects of Newtonian gravity, or one or two aspects of gravity from the Newtonian perspective that is unique, and it only applies to gravity. For instance, you know that Newton's laws of gravitation tells you what is the force, magnitude of force experienced by a test charge, small m, due to another object of mass, capital M. And you know the formula by heart, F is equal to gm capital M small m by r square. R is the distance between the two masses. So this force leads to an acceleration because force leads to an acceleration of the test mass, and you can write this force, equate this force to mass into acceleration, right? M into d square r by dt square will give you the force. So now if I equate these two equations, that is m d square r by dt square is equal to gmm by r square, then you will see that you can cancel off this little m's, and you will see that the acceleration that this force exerts, that is the acceleration that the gravitational force exerts, is independent of the test mass, right? This is unlike, so let me repeat. So if you can cancel off this little m's on both sides, and you will see that the acceleration experienced by the mass is actually independent of the proper nature of the mass. This is unlike any other forces. For instance, if you take electrostatics, you can write similar equations, right? So because m into d square r by dt square, which is the Newton, which is given by the Newton's second law, is equal to 1 by 4 pi epsilon 0 q by r square. And you will see that the nature of acceleration is, you will have to take this little m to the denominator of the right hand side, and you will see that the nature of acceleration is proportional to small q by m, right? Or in other words, the acceleration depends on the charge to mass ratio. So this is a unique property of um, of uh, of gravity. So now I will actually request organizers to share this video. Um, uh, right. So this is a video. I will unshare my screen. Um, so Aditi.
Yes, sir. Just give me a minute. I'll open it.
Sure. So basically, this is a video of. You might have seen this video in other location, but it's cool to watch. So we will watch it again. For those who haven't watched, then well. So this is basically they take two objects. One is a feather, and another is a bowling ball. Clearly, bowling ball is much heavier than a feather. So they try to, they take it to a height and drop them from the same height, and then they watch them fall. And in the presence of air, you know that the feather will fall more slowly, but in vacuum, you will see that both these objects fall together at the same rate. And this is why this is what we saw just now in our in the slide, that acceleration is independent of matter, and
So,
independent of the nature of the test mass. Aditi, start sharing.
okay, I'll start playing.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
So now this is motion in vacuum. So as I was explaining, the mass, the acceleration that is experienced by a test mass is independent of the gravitational field that is present. Independent of the acceleration experienced by the test mass is independent of the nature of the test mass. It only depends on the nature of the gravitational field that is present. So this is unlike any other forces. So this led so this can be so basically this what this tells us is that gravity is unique. Gravity does not depend on the properties of the particle under consideration. Then it is everywhere, it cannot be shielded. Also there are other properties such as if you drop an object on the ground, which is the guy on the right hand side. So if the ball is dropped, then on Earth this person will measure an acceleration due to gravity, right? Acceleration. The ball will fall with an acceleration due to gravity. Now, if he is actually on a rocket, which is accelerating upwards with the same acceleration due to gravity, then also if he drop a ball, he will not be able to. Uh, he will say that this person will say that the ball is falling with the same acceleration, which is acceleration due to gravity, 9.8 meter per second square. So this tells you that this person, by experimenting with gravitation, he will not be able to tell apart whether this person is. So the effect that he is observing, that is the falling of the ball, is due to gravitation or due to him being in a particular frame of reference, right? So this being in a rocket is, I will take that to be in a particular frame of reference. All these ideas took Einstein, and actually he already had by that time. Okay, so all these ideas made Einstein to come up with general relativity. More importantly, he had already discovered, he already come up with special theory of relativity, and in which he knew that forces cannot be instantaneous. Any signal in the universe will travel with at most the velocity of light, and he needed to come up with a theory which obeyed that principle. It's because Newton's gravity doesn't tell about anything about when, how long does a gravitational signal take time, I mean take to travel from one place to another. So this made Einstein to come up with general theory of relativity. So basically he actually starting 1905 when he came up with special theory of relativity. After that he spent like 10 years working on this. So in between, he came up with several equations, several versions of gravity. He learned a lot of mathematics during that time. Um, so he described those years, those 10 years, as the most. The most he had worked. I mean, he worked a lot during those 10 years. Yeah, he learned a lot of new stuff. He came up with a lot of new stuff. So basically he wrote this equation: g mu nu is equal to 8 pi g t mu nu. So it is a very concise equation, and I will try to explain what this equation means. Basically what he meant is that the left hand side is basically describes the geometry of the universe, of the space time, and right hand side is consists of the matter content in the space time. So he equated these two and said that the nature of the space time will explain, so basically this equation will explain what is gravity. So let's try to understand this equation a little bit more details. So g mu nu is basically called as Einstein tensor, and that quantifies geometry. T mu nu, on the other hand, is the energy momentum tensor, and that describes the matter content causing the geometry. So you don't need to go into details of how to derive all those things, but qualitatively we will understand that left hand side quantifies the geometry, and right hand side quantifies the nature of matter content. Okay, so basically if you take this equation and go to the Newtonian limit, so in that limit you will get back Newton's force of gravitation. So this equation you has this tiny mu, suffix mu nu. Basically what it tells you is that this is actually for a 4-dimensional space. So there is 3 dimensions of space and 1 dimension of time. So each mu and nu can take t values, time, and 3 directions, which means that it's a 16 by 16 equation. So you can write g00, which is basically the time component, and so on. So there are this is time space, time x component, time y component, time z component, and so on. So basically this equation is actually 16 equations. So for instance, g00 is equal to 8 pi g t00, g22 is equal to 8 pi g t22, g31 is equal to 8 pi g t31, and so on, right? So now let us try to understand what is the a little bit more about geometry. So if you take a piece of paper or the screen that you are looking in, it is flat, right? So in two dimensions, you have a flat screen, and the geometry of that screen is described by just looking at the distance between 2 points. So if you look at, as far as Einstein's relativity is concerned, you can just describe the geometry by the distance between these 2 points, x1, y1 and x2, y2. So if you know from Pythagoras theorem that if you want to know the distance between these 2 points, you can basically what you have to do is you have to write dx square plus dy square. And I can write, if you know a little bit of matrix multiplication, then you know that dx square plus dy square is equal to dx dy 1001 dx dy. So if you multiply this and this together, you will obtain a column vector with dx and dy. And if you multiply this and the column vector that you obtain, you will obtain dx square plus dy square. So this quantity, which is 1001, or and this equation can be written in this manner: sum over a b g is equal to 0 to, it's not 0 to 2, it's 1 to 2, because there is only two direction. There's a mistake. So a comma b equal to 1 to 2 g a b dx a dx b. So it can be g11 dx1 dx1, g12 dx1 dx2, g22 g21 dx2 dx1, and g22 dx2 dx2. Of course g12 and g21 are 0 from this matrix, and you have this form. So this GAB is known as the metric tensor. So what I have said so far, so G mu nu is what quantifies the geometry of the space-time. Basically, if you by geometry, what I mean is basically if you know how is the distance between 2 points represented, and that distance is in order to describe the distance, we bring in some quantity known as the metric. So this metric, so this G mu nu that you saw in the previous screen is a function of GAB, the metric tensor. So if you know the metric tensor, you have described the geometry. So there are, depending upon the nature of the problem, you can consider various types of geometry. You can have a sphere, which is a positive curvature space-time. You can have negative curvature geometry, and you can have a flat geometry, which is the surface of the sheet. Now, so now basically what this equation tells us is that left hand side, as I told you, describes the geometry, and the right hand side tells you about the matter content of the universe or the space time. So basically this equation, what it tells is that matter causes the space time to curve. So you have matter on the right hand side. If you are given the matter, then that will explain what is the geometry on the left hand side. So there is only also one more equation which is equivalent to the force equation, because when we described Newtonian gravity, we discussed two equations, right? One is the force equation, which is gmm by r square. Another equation tells us what is acceleration. So md square r by dt square is equal to force. So similarly, uh, there is an equation of this form, right? So here d square x mu by ds square, s is some parameter, and x mu is the trajectory taken by some particle in the space time. And this green term describes the curvature of the space time. So if you put this gamma mu alpha beta, which is describes the curvature, to 0, you know that d square x mu by ds square equal to 0 is the equation, and that equation is actually the equation of a straight line, right? If you put gamma to 0, you will get a straight line equation, because why? You have for a straight line you have constant slope, and if you take one more derivative, that d square x mu by ds square will be equal to 0. So basically there are two equations, right? So this equation, what it tells us that due to the presence of this green term, which is the which describes the curvature of the space time, this makes this straight line motion curved, right? So this is what causes the earth to go around the sun, or our Milky Way to go around our galaxy, sorry, a solar system to go around Milky Way, and so on. So basically this equation tells us it tells us is that curvature decides how matter moves. Now how much, oh, I don't have much time. So, but then if there are questions, this is a good time to ask. Basically GR tells us is that matter tells spacetime how to curve, and curved spacetime tells how matter to move. Are there any questions at this point? To summarize what we have done, we have we have described our universe. Basically, it is homogeneous, isotropic, expanding. Then we discussed what are the various matter content. We have non-relativistic matter, we have radiation, we have dark energy, and so on. And then I told you that our universe is actually governed by general theory of relativity. Sorry, gravitation, and gravitation is best described by general theory of relativity. And I told you that basically it relates geometry to the matter content, and basically the geometry is described by something called as a metric tensor, which is basically responsible for telling us how far apart are 2 points. So, or it tells us the distance between 2 points. So this is what we have learned. Okay, so may I proceed? Am I still with you?
Yes, sir. Just a
Okay.
moment, sir. There's 3 questions in the chat, sir.
Oh, okay.
So I'll read it out to you if you don't mind. Okay, so the first question is by Jishnu Das. So how did they distinguish between dark matter and energy, sir?
Matter. Okay, so basically matter is they have different gravitational effects. So dark matter behaves like ordinary matter in the sense that it is pressureless. I told you, right? So I shared a pie chart, and basically dark matter behaves like ordinary matter as far as gravitational effects are concerned. So it doesn't have any pressure. It doesn't have any pressure. On the other hand, dark energy is a different animal in the sense that it has a negative pressure, and if assuming that in our universe, I mean, if you have dark energy in our universe, you will see that our universe will undergo accelerated expansion. We will, yeah, it will undergo accelerated expansion. So their gravitational effects are different. So this is how we know.
Yes. So the next question is mine. Aren't isotropic and homogeneous the same concept?
No, right? Homogeneity means that it looks the same at two different points. So if you are here and then you go to Bangalore and then look around, if both places look alike, then you will say that it's, I mean, Karnataka is homogeneous. But if you look in the direction to the sea, if you look west and you see sea from Bangalore, and if you look east, and then you see a hill, then you say that clearly it's not isotropic, right?
Okay, so does that imply that isotropic, if something is isotropic, then it must be homogeneous? Does one imply the other, sir?
I don't think so. You can break isotropy and still have a homogeneity. How can I see that? Yeah, you can. In principle, you can actually break just isotropy and still have homogeneity. The way to see that, I'm not coming up with a good example. I don't have a good example with me, but yeah,
Yes,
in principle, you can have a different.
Okay.
You can just break isotropy. You can have that.
And there's a few more questions, sir. Rakshitas, Bernard Riemann had the ideas that gravity was curvature of space but not space-time. From a historical point, is it true?
I actually don't know. Riemannian geometry was known. Yeah, maybe Riemannian geometry was known, and in fact, it is the Riemannian geometry that Einstein used. Probably it is true. But the point is that mathematically these techniques existed, and I think there was a person called Marcel Grossman who introduced Einstein to all these techniques. That there are these techniques that you can use, and what I have heard is that he was instrumental in introducing Einstein to many of these techniques, and then Einstein studied them and eventually used it in this context.
And Shobhuj asks, why does the affine connection correspond to curvature?
Why does? Oh, basically it is a first derivative of the metric. Connection is derived from the metric. So if you are, and in a curved in in a flat space with no curvature, that quantity will be 0. So in that sense, yeah. The next question: does the mass cause the formation of curve? Mass curve in the graph obtained by metric tensor is the gravitational field. So we assume, I mean, so when I described a Newtonian, okay, no. So Rakshit, I have answered all. I mean, I tried to answer your question, but okay. So basically, what Sreenath's question, that is, yeah, you can have. When I explained this Newtonian gravity, where the little m cancels off. So basically, there is a gravitational field which is given by gm by r square, and yeah, so that is responsible for the gravitational field. And when you have particle moving around, so the nature of the motion of the particle is not dependent on the property of that particle, but the mass, the gravitational field that is created by it is created by some mass, right, in the Newtonian view. So that mass is responsible for the gravitational field it creates. So in Einstein's equation, you have g mu nu is equal to t mu nu. So there is some matter on the right hand side, and that creates a magnetic field, and on the other, gravitational field, and that is described or creates a curvature, and that curvature in turn influences the trajectory of this matter. Okay. I am rushing because we are short of time. We need to still get to the universe part of this lecture. So Jupiter having greater gravitational, why it is not affecting? Okay, so I actually don't know okay, so we will okay, so thank you for this last question actually. So basically, when we consider a system, so this in this lecture I will not get to this question. So so basically, when we study a system, any system for that matter, we will consider forces that are to scale with that system, in the sense that when we consider our universe, we don't consider solar system or what happens in solar system. We actually we can in fact consider, say, a galaxy as a single point. In if you try to simulate a universe in a box, you can take galaxy to be a single point, right? So we will take this attitude that we are only interested in the physics at the largest scales. So this is basically the distinction between cosmology and astrophysics. So basically, in cosmology, you actually are concerned only with the large scale behavior of our universe, whereas in astrophysics is something where you actually go into detailed in modeling or understanding each system in detail, in the sense that if you want to study a star, or if you want to study the say, for instance, the magnetic field created in a solar system, or what is the sun, so what is the, how do you study the or understand the solar cycle. So all these things are part of astrophysics, and when you study cosmology, you consider the universe to be as a universe is your system, and you study only the large scale effects, so that you don't lose track of the big picture of the universe. So actually, I haven't answered your question about Jupiter, and I actually don't know. I have to read it up. Okay, so let's move on, and so we have learned the basics of our universe, and now let us apply it to our universe. So basically, you need a metric to describe our universe, and I will state that our universe, assuming it is spatially flat, it is to a large extent it is. So our universe is described by this metric: ds square is equal to minus dt square plus a square times dx square plus dy square plus dz square. So this metric is known as Friedmann-Lemaitre-Robertson-Walker metric. Now let us try to understand this metric. So this metric contains time, which is minus dt square. Then there is 3 spatial direction, dx, dy, and dz. And then there is this factor which is multiplying dx, dy, dz. Basically, this factor is known as scale factor. So what it does is, as time proceeds, this factor will keep on increasing. This factor will keep on changing. So if this is increasing, then you will say that the spatial part of this metric, that is dx square plus dy square plus dz square, is increasing because you are multiplying it by a square. So if you consider these 2 points, these two are galaxies, and it is separated by 2 cells, right? 2 cells. What it does is, so this 2 cells, since it is separated by 2 cells, you will say that they are 2 units, 2 meters, or 2 megaparsec or something away, 20 megaparsec away. And then now you say that after a time t, a of t1 would have become bigger. So this box would have stretched and become a bigger box. And these two cells are still sitting at the respective location, but the thing is that the distance between them have increased. So now the 2 units that is there would have become 2 times the physical distance between these two galaxies would have become 2 times a of t2 divided by a of t1, right? So because the expansion, so this would have expanded to a factor a of t2 by a of t1. So the a of t, this factor a of t, which is known as the scale factor, captures the expansion of the space. It's because a of t keeps increasing as the time evolves, and because of that, we'll see that the universe is expanding. Okay. So now I take this metric. Remember, this metric captures the geometry, and the most important geometry is it also captures homogeneity and isotropy, because there is no preferred direction in this one, and also it doesn't. If this dx was actually a function of, say, y or x, y, z. Similarly, there was some function in front of this which was a function of x, y, z. Then I would have said that this is inhomogeneous. Or this is not homogeneous. And if suppose dx and in front of dy there was some extra factor, or if suppose the scale factor was different in front of different dx, dy, dz, then I would have said that universe is isotropic, because no directions are treated the same. Here directions are treated the same, and this function doesn't depend on location. This function is not, this right hand side is not a function of where it is located. And I believe, Rakshit, this answers your question also, because I can have a function multiplying this scale factor which depended on x, y, z. Then I would say that this metric is inhomogeneous, because at different values of x, y, z, the metric will be different. On the other hand, it will still be isotropic, because all directions are treated the same. It is just that when you go from one place to the other, the quantity in front of this will be different. Now, if instead of, so that is inhomogeneity. Now, if you want isotropy, what you would need is that this factor should not be common to all directions. It should be separate for each function. So there will be, so for instance, you can have a1 of t multiplying dx square, then you can have another a2 of t multiplying dy square, and then another a3 multiplying dz square. Then you would say that your space-time is anisotropic. But there are other forms of anisotropy also, and I think there are works which describe what are the different types of. There are classification of anisotropy and so on. But anyway, so this is basically, this metric captures the expanding nature, homogeneity, and isotropy of our universe. So now what you do is you take this metric, put it in Einstein equation, and then get out what is known as Friedman equation. Basically, the only dynamical quantity, which means only time dependent quantity in this metric, is a of t, and we will get functions, equations containing time derivatives of a of t. So in this equation, you have, I will explain various terms. You have two equations, right? So the a dot here is actually dA by dt. A double dot is actually d square a by dt square, which is the second derivative of a, scale factor. Rho is actually the energy density of matter, and P is actually the pressure of the matter, right? So this is the basically Friedman equation. As I told you, right hand side, which is energy density, pressure, all those things are quantities describing the nature of the matter content, and the left hand side describes the geometry. In this case, the geometry, basically by geometry what we mean is how is it expanding, or how it is changing with respect to time. So this is the these are the Einstein equation, or what is known as Friedman's equation, Friedman equations, because Einstein equation in the context of expanding space-time. So now we need to so good, we have got some equations. We know that on the right hand side we have energy density and matter. Remember our classification, because we told you that we saw that pressure is for non-relativistic matter we have zero pressure. For radiation we have a pressure and radiation sorry, pressure and energy density are related in this manner, and in dark energy pressure is equal to minus rho. And now what I will do is I will just focus on the first equation. Let me hurry because we are over time. So the first equation, a dot by a whole square is equal to 8 pi g by 3 rho. I'll take that equation. I'll just focus on that equation. So this a dot by a is known as Hubble parameter. So if you measure that, it is called a parameter when we measure it today, because this value is can be treated as a constant today, because our lifetime is nothing compared to the lifetime of the universe. So h is a constant. So this but over time, if you take the history of the universe, h is actually vary with respect to time. So this is, and how the universe varies with time is what we will find out. So basically this a dot by a tells you the rate of expansion of the universe, and we will try to study the rate of expansion of the universe. And as you can see from this equation, the rate of expansion of the universe will depend on the energy density of our universe. And the energy density of our universe, as you can say, as you have seen, can be split into three components. Energy density due to gamma. Gamma is radiation. Basically gamma stands for radiation. Then energy density due to matter, which is rho m, and energy density due to cosmological constant or dark energy, which is rho lambda. So there are three components of energy density. One is due to radiation, the first term; due to matter, which is the second term; and third term is the dark energy. Now you should note that each of these components depend on time, and because of that, at different times your nature of scale factor or derivative of scale factor will change. So let's see how this is done. So basically I told you that our universe is expanding. So so any distance L between 2 points in our universe gets stretched as time passes. So basically you can say that any distance L is proportional to scale factor. So as the universe expands, a of t increases, and so does distance L. So keep this in mind. So any distance, whenever you see a distance, you should keep in mind that as the universe expands, that distance will increase, right? So now if you look at this equation, which is the Friedman equation, you will see that there is a rho m of t. Rho m of t is basically energy by volume, and energy by volume. So basically volume is proportional to L cube, and because any distance L gets stretched as a function of scale factor, sorry, stretched by scale factor, you can see that the energy density of matter is inversely proportional to 1 over a cube. So if you know the energy density of matter today, which is rho m of a naught will be the scale factor today, then you can write the energy density at any time in the past by this relation. Because if you have energy density rho m of a naught today, then since it's proportional to inversely proportional to a cube, you can just find the a cube value at some time in the past, and then you know what is rho m of t at that time. Fine. Similarly, if you take radiation, right? So if you take radiation, which is rho gamma of t, this is also equal to energy by volume, and you know that energy is basically h nu of radiation is of a photon energy is h nu, and h nu is basically hc by lambda. So lambda is the wavelength, and lambda is wavelength is also a distance, and it will also get stretched as the universe expand, which means that this term is inversely proportional to fourth power of distance, which tells us that this term is inversely proportional to 1 over a raised to 4. Let me repeat. The matter had energy by volume. Volume is proportional to L cube, which means that L cube is proportional to a cube, which means that this energy density is inversely proportional to cube root of scale factor. Sorry, cube of scale factor. On the other hand, when radiation is there, radiation energy is given by hc by lambda, and lambda is a function of, lambda is also a length. So this energy density of radiation is inversely proportional to fourth power of scale factor. Now finally we have one term which is rho lambda of t, which is basically due to dark energy, and dark energy is actually a cosmological constant. So it doesn't depend on time, and you have a constant. So when you want to write, so you can write the first Friedman equation in this manner: 8 pi g by 3 rho gamma by a raised to 4 rho m by a cube plus rho lambda. I will take a few more minutes and conclude. So these are the three terms in the Friedman equation. Now I will just massage it a little bit. Basically, I will divide by the Hubble parameter today, square of Hubble parameter today, h square by h naught square, equal to 8 pi g by 3 h naught square times whatever was there in the bracket. And I can actually take this quantity on the outside this bracket and absorb it into rho gamma, rho m, and rho lambda, because this is constant. You can absorb it into these quantities on the numerator, and you can write an equation of the form h square is equal to h naught square omega gamma by a raised to 4 omega plus omega m by a cube plus omega lambda. And h here on the left hand side, h naught is the Hubble parameter today, but h is the function of scale factor. So as you go to the past, scale factor will become smaller and smaller because our universe is expanding. So in the past, our universe would have a smaller size, which means that in the past our scale factor will be small. Which means so basically h is a function of scale factor. So let us now try to understand this, how the universe would behave for from this equation. So we will try to understand how the universe will expand, how the rate of expansion will change as we pass. As we play back our universe to the past. Okay. So for this, what I will do is I will just look at this terms in the bracket, right? And this bracket has three terms. Each has a different dependence on scale factor. All these functions, omega gamma, omega m, omega lambda, are constants. So on the right hand side, I will plot omega I of a. Sorry, on the y axis, I will plot omega I of a. Omega I can be omega I of k can be omega gamma by a raised to 4, or omega m by a cube, or omega lambda. And on the x-axis, I will plot scale factor. So scale factor, as you know, because our universe is expanding, it can be considered as a time, right? So if you take, if you say that the size of the universe of the scale factor, if we fix the value of scale factor today to be 1, so here is today, and then as we go to the past, the scale factor will keep on decreasing because the universe was smaller in size in the past, right? So this is the past, this is today, and this is the in this axis I will plot each of these terms. So let's plot the simplest one, because the last term is a constant, so I will have a constant black line. I have tried to use the exact values that we obtained, I showed you in the pie chart, but anyway, so this plot, this line corresponds to this omega lambda, right? Now if I plot the second term, which is omega m by a cube, the a cube behavior, 1 by a cube behavior is shown by this blue curve. And if you plot the third term, which is omega gamma by a raised to 4, which is the red term. As you can see, as you can understand, 1 over a cube grows to the past faster than the constant term. But 1 over a raised to 4 becomes very large as we go to smaller and smaller values of a. For instance, 1 by 10 raised to minus 5 whole raised to 4 is like 10 raised to 20, whereas omega m by a cube, 1 by a cube is only 10 raised to 15. So clearly in this domain, this red line will be larger than the blue line, whereas here blue line is larger than the red line, and here today the black line is larger than either of them. So so this figure tells us that today we have this expansion of the universe is dominated by omega lambda. So we call that as lambda d, which is lambda domination. Our universe is dominated by lambda, cosmological constant, or dark energy. So today our expansion is dominated by dark energy. Sometime in the past, our universe was dominated by matter content, right? Non-relativistic matter content, like electron, proton, all ordinary matter, dark matter, and so on. And if we go further to the past, to the oldest epochs, you will see that our universe was actually radiation dominated, because this red line, which corresponds to the radiation, was dominant. So this is why we say that our universe, if you take our universe into the far past, our universe is dominated by radiation. So we say that our universe was hot and dense. Because why is it called dense? Because the size of the universe is was small, much smaller than today, and because all the matter that we know today was packed into that size, you know that universe was much denser in the past, and it was hot. So this hot phase of our universe is known as the Big Bang. Um, so I will not go back further. Further, there are many more interesting issues and that which needs to be addressed. But basically, we say when we say that our universe started with a hot Big Bang, what we refer to nowadays when we say Big Bang, what we refer to is this phase of the universe where our universe was extremely hot and dense and dominated by radiation. So to in summary, what the simple model of universe, and actually this just one equation, tiny equation, has already told us a lot, right? Our universe started with a hot radiation phase, then it slowly transitioned into a matter dominated phase where the matter density was dominant, and today our universe is actually lambda domination. In fact, what you can do is that you can play with these equations, use the equation of state, that is the relation between pressure and density, and actually compute what is the rate of expansion in each of these phases of our universe. So you will see that the rate of expansion in during radiation domination and matter domination is in fact decelerating. So the universe decelerates. It doesn't. I mean, the expansion nature of expansion is decelerating. Whereas you will see that today, because of lambda domination, dark energy domination, our universe is actually accelerating. Okay. So this is what. This what I presented is only a simple model, which is known as the Friedman model. Actually, you can add in a lot more complexities, and this is the picture that we have today. So we believe that our universe started with Big Bang, singularity. I mean, so initially there was a, because we can't push our understanding beyond a certain point because of our limitations of general relativity, uh, and because of lack of information from those regimes. So we have not been, I mean, we are trying to push, but we have not been able to push beyond a certain limit. um, uh, so we believe that our universe was started from a I mean, we had an early phase of inflation, which and then that led to several initial conditions, which led to the formation of the universe as we see today. So there was a radiation dominated phase here, and we see the remnants of that radiation today as CMB, cosmic microwave background. And after that, several ages passed. These are known as dark ages because there were no stars at that time, and universe was was not dense enough. So you will not see anything. Light was actually streaming freely. There was nothing that could scatter light, and because there is no star, there was no light at that time. In the sense that there is nothing scattering the light, so it is called a dark age. And eventually the stars started forming, stars and galaxies started forming, and we have what we see today, right? um, uh, what we see today. So this is the picture of the universe that we have arrived at, and there are many open problems, and I urge you to learn more and contribute to this exciting field. Thank you. There are a few references, I mean, a couple of references that are interesting. You may want to go through them as well. Thank you.
Okay, sir. There's one question in the chat. Sreenath asks, if you take universe spatially flat, how can it have three components? Should it not only have two? Does this mean that universe expands only in one direction?
Oh no. So I no. Spatially flat in the sense that in 3 dimension, I will assume Euclidean kind of geometry. So it just means that my spatial components, if you take 2 points, distance between 2 points, I have the distance is dx square plus dy square plus dz square, and of course there is an expansion factor, but otherwise it's just dx square plus dy square plus dz square. It's not more complicated. So I told you about spatially flat in case of flat surface in the case of 2D, but you can consider the same for 3D. You just have to add one direction, right? So let me take you to yeah. So in 3 dimensions you can have spatially flat in the sense that if I add plus dz square, then also I would call it spatially flat. Uh, because GAB will have one more one in the diagonal. It will be 3 by 3 matrix with I mean 3 by 3 unit matrix. So that is all what I meant.
Okay, so then Rohan asks, we assume that we start from singularity, don't we?
Yeah, I mean we don't say that we start from a singularity because hope is that quantum gravitational. So basically the hope is that very far in the past. Um, um, there will be quantum gravitational effects that will take up that will become more dominant, and eventually it will address the problems about I mean it will address the issues with singularity. So this is a work in progress, but there has been some proposals. For instance, there is something known as loop quantum cosmology, where using whatever we using our understanding of quantum gravitational I mean certain principles of quantum gravity, what people have suggested is that universe may not, as universe go further to the past, it will reach a minimum size at some point, and then in the past, towards the past, it will be still be towards the past the universe will be larger, right? So you will see that the universe was very large, then it decreases, it becomes small, and then to a minimum size, and then it will start expanding again, and this we are in this expanding phase to the right. So this is known as bouncing scenarios. So there are not only quantum gravitational bounces, but there are other bouncing models that have been proposed, and people are exploring I mean, so it is not enough in cosmology. It is not enough to propose a model. It is also important to test them with observations. So the current major goal of today's research is to understand whether we can say something about the early universe. I mean, about this close to singular phase of the universe. It should not be singular, but I mean it may not be singular, but we are trying to understand whether that phase can leave some signatures in today's universe, which we can observe.
And Srinivas adds to his previous question, sir. Sir, does this mean that expansion happens in the r vector direction?
Yeah, I mean, there is no direction preference. So if you take any two distances, any two points, so the space between that, you have to understand that the space between those 2 points are expanding. So yeah, if you fix, which means that if you come with a coordinate system and you are at the center of the coordinate system, all points around you are expanding. So which means you can take it as in the r direction. Anirudh was.
A lot of science shows say that these equations break down at t equals 0. What does this exactly mean, sir?
The scale factor goes to 0, which means that and when scale factor goes to 0, the Einstein equation, the Friedman equation that I wrote down, it doesn't behave well. Yeah, so here if denominator blows up, denominator goes to 0, this equation kind of blows up, right? H goes to infinity. So that is the problem. If the numerator still remains 0, and also then what happens to the rho has to somehow mysteriously vanish. So all these issues are there. So when a goes to 0, then this equation is not well behaved. This is what we mean. So actually I think modeling our universe, I mean, so as you have seen in this talk, it is a very simple model, right? So all I mean, which is something we could describe in like 1 hour 15 minutes, right? In 75 minutes, we could describe a tiny model of our universe, and universe is so big, and it's very simple to describe. Of course, there are details, and details need to be worked out. For instance, there are many open problems. There are several open problems. We don't know about 95% of the universe, or we don't know much about very early universe, and we are still to work out the details of how each galaxy form. Why do galaxies have different shapes? Why are galaxies distributed in the manner it is distributed, and so on. So those things are details that we need to work out. But because of ever improving technology, analysis methods, and so on, it is actually a precision science. You cannot sit at some place and then just come up with models and be done with that. It is actually a precision science. There is a lot of you need to actually observe something and establish your theories, and you are able to do. And the errors that people talk about these days is like sub-percent error, 1% error. If you need such excellent measurements to prove your theories. So welcome to this. Those who are interested, welcome to this amazing field. Yeah. Over to the organizers.
Just a moment. Rohan has one last question to add. Is the cause of inflation known or still yet to discover?
So no, inflation is actually you would say something. It is a paradigm in the sense that inflation is like a okay, so it's a class of there are a class of models that you can make that you can come up with basically. Okay, so those who, not all of you will know what is inflation. So basically what inflation tells us is that very early in the universe. So I told you about and I told you about a very simple picture of the universe. Basically, universe is homogeneous, isotropic, and so on. But in reality, matter is not distributed homogeneously and isotropically, because there are us. There is a planet Earth. There is a galaxy. Then there is a large space between two galaxies. So it's not exactly homogeneous. So there are tiny inhomogeneity in the universe. And in order to create a tiny inhomogeneity, we need a initial condition. Initially, there should be some tiny inhomogeneity in the early universe. Then only as the universe expands, because if the gravitational force field was exactly the same at all points, the matter will not clump together and form galaxies, right? So there were places where gravity was strong. There were places where gravity was weak. Wherever the gravity was strong, dark matter fell into that gravitational trap. It strengthened the field at those points. Then more hydrogen, everything fell into that potential well, and eventually the stars and galaxies was formed. So you need a certain initial conditions which tells you how gravity how I mean, we need certain initial conditions, certain tiny inhomogeneities at the very early universe. Inflation provides a possible way to explain that, give you that initial condition. So what we can say is that there are several models of inflation. And also inflation refers to a very accelerated expansion at that time. And there are several models that has been proposed. And currently people are trying to arrive at least a class of models which can narrow down the model of inflation. So there some progress have been made, and there are several experiments which are planned in the future, which will hopefully constrain inflation. But again, so the inflation is a broad platform of models, and you need to come up with a. And there are also inflation is also not a complete model, complete scenario. It can be broadly classified as a scenario, where and you need to work out the details, and that is still in progress.
All right, then that's all the time we have actually. So, yeah. Silpashree, can we wrap the meeting up with a quick vote of thanks.
Yeah, I would like to thank Professor V. Sreenath for such a wonderful session. It was very informative. Thank you, sir, for giving us your time during your busy schedule. Next, I would like to thank all the audience members for attending the talk. Hope you found it useful and you enjoyed it. I would like to thank Astronomy Club for hosting this talk and giving us an opportunity to learn more.
Thank you all. Yeah, meet you some more. Bye.
Thank you so much,
Thank
sir,
you,
for your
sir.
time.
Thank you, sir.
Bye.